Hey everybody, today we're taking a look at trig functions. We're going to review the basics of them. We're going to talk about how to find the derivatives of the initial three, sine, cosine, and tangent. But we're also going to talk about the derivatives of the secant, cosecant, and cotangent functions as well. And we're going to then incorporate that into the other derivative rules that we've already been discussing. And by the end of this lesson, we'll have a pretty good understanding about derivatives with trig. So when we talk about trig, we want to make sure that we recall that one full revolution around the unit circle is 2 pi. And anytime we're talking about any specific point P, we can find the coordinates of that point by looking at the cosine of t, comma, sine of t. That's just referring back to all the other things that we've talked about with trig leading up to this point. Now, eventually we'll get to talk about all the applications of why we might want to know the derivative functions for these trig functions. But for now, we're just going to briefly introduce the idea of angular velocity. And it says here the angular velocity is the rate of change of angle AOP with respect to time. So basically, we're looking at the unit circle over here, and how quickly are we going around this unit circle? And when we talk about at a specific point P, a derivative function will give us the slope of the tangent line there. And we've talked about looking at circles before when we were talking about the derivative for other types of functions. But today we're focusing really on the trig functions. So whether we're looking at the angular velocity, which is going to be the change in one variable and the change in the variable, we can also refer to that as linear speed, dl dt. So how quickly is L changing with respect to t, time. So like I said, we'll talk more about the applications moving forward, but we're really focused today on finding the derivatives, and then once we understand those, then we'll go ahead and apply them into our actual problems. Now, I don't know why my pi symbols don't appear to want to be showing up in this table here. What we're going to be looking at is y equals sine of x. You can go ahead and plug that into y1 into your calculator. And then what we're going to do is we're going to find different points on the curve and then find the dy dx, find the derivatives at those specific points. So we see we're looking at pi, I should say pi over 2, pi, 3 pi over 2, and 2 pi. And you probably don't even need a calculator to find these values here, but when x equals 0, the sine of x equals 0, then we go up to 1, we come back down to 0, down to negative 1, and we're back at 0 when we look at x equals 2 pi. And just to kind of refresh yourself, if we were thinking about this on a coordinate plane, the sine function would start here at 0. It would go up to 1, back down to 0. It would go down to negative 1, and then finally get itself back here to 0 when you got to 2 pi. So just kind of filling in, we had pi over 2. There's pi, 3 pi over 2, and 2 pi. Now, when you look at that function, at least 2 of those, you should be able to tell me what the derivative is without even going into your calculator. Specifically, when we look at the point right here, pi over 2. If I look at pi over 2, the function y equals sine of x is completely horizontal, so the derivative is going to be 0. And where else is that the case? Right here at 3 pi over 2, the derivative is 0 as well. And then if you wanted to find the derivative at the other values for when x equals 0, pi, and 2 pi, again, you can have the calculator do that for you. Second, calc, and then select option 6, dy dx, and then just go ahead and plug in those x values that you're concerned with. When you do that, you end up getting 1 as the derivative at x equals 0, and you end up getting negative 1 at pi, and positive 1 there at 2 pi. Now, if you think about those points, and you were to represent x versus dy dx, well, it kind of looks like another trig function. Specifically, 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, and 2 pi 1. If you were to graph that function is the cosine curve. So if I'm looking at y equals sine of x, dy dx is equal to the cosine of x. And you can find more points to confirm that, but that's the general idea. If you have y equals sine x, the derivative function is the cosine of x. Let's do the same with cosine of x. So we just showed you what cosine of x looks like. It starts at 1, goes to 0, goes to -1, comes back to 0, and then goes back up to 1. With plugging in those values there again, pi over 2, there's pi, there's 3 pi over 2, and there's 2 pi. All right, so, whoops, we have a little bit of a typo there. That should say cosine of x. We're going to plug now y equals cosine of x into your graphing calculator, and we're going to look at those values for its y values and also for its derivatives as well. So plugging in the y values, well, we kind of just did it up on the graph. Now we're just going to transfer here. There's 0. Again, my pi is not working. 3 pi over 2, and that's 2 pi. So for pi over 2, y is 0, -1, 0, and 1. Just as we did before, there are some derivatives that should jump out at you. Pi is the most obvious one because you can see both sides of it there. So the derivative at pi is 0 because it's horizontal. But you could also see at 0 and 2 pi. If I were to continue the graph, you would see that as well, that those derivative values are 0. So then you're really just looking for what's the derivative here at x equals pi over 2, and what is it here at 3 pi over 2. Based on what we just saw in the previous investigation looking at y equals sine of x, you might be able to guess that the derivative at pi over 2 is -1, and at 3 pi over 2 is +1. Okay, so now we're looking, we have, again, x values and the derivative values. Let's go ahead and plot those and see what we see. We have 0, 0. We have pi over 2, -1. And then we have pi 0, 3 pi over 2, 1, and 2 pi 0. So if I were to look at that graph, it looks very similar. Now, you might be tempted to try to think of this as the cosine curve translated, but instead, let's look at what else it could be. We're starting at the midline, the principal axis here, and we're going down. If we were starting at the principal axis and going up, that'd be the sine curve. But if we're starting at the principal axis and going down, well, that's something else that we talked about from Trig. That is the negative sine curve. And that's really what we're talking about here. So if we have y equals the cosine of x, the derivative function is y equals the negative sine of x. So now we have 2 of our 6 derivative functions down, and here they are. We said if we have y equals sine of x, the derivative function is the cosine of x. And if we have y equals the cosine of x, its derivative function is the negative sine of x. And those are pretty basic ones, pretty easy to learn and understand how they come about. Good news, these derivatives, as well as all other trig derivatives, are available for you on the formula notebook. So you don't have to have them memorized, per se. So we talked about sine and cosine. The third basic trig function is the tan of x. Now we could go through and we could try to identify what the trig function or the derivative function for tan of x is going to be using our analysis that we just did. But this one's a little bit more complicated. So let's look at it from a different point of view. Let's think about the tan of x and understand that that's the same as sine of x over cosine of x. At that point, we can look at it and say, all right, well, I have one function divided by another function when I'm looking for its derivative. That's really just an application of the quotient rule. And if we remember the quotient rule, that is going to be u prime times v, when it's u times v prime, over v squared. And if I were to write this out, let's see, u is going to be sine of x. U prime, we just established this, is cosine of x. V is the cosine of x. And v prime is negative sine of x. So we could take that information and go ahead and plug it in right here. All right. Now, once we do that, then we can go ahead and do some multiplication. So we have cosine of x times cosine of x, that's cosine squared of x. negative sine of x times negative sine of x is sine squared of x. And we should recall our most basic trig identity that says sine squared x plus cosine squared x equals 1. So we see that 1 right there that we can substitute in. And then we understand we have 1 over cosine squared is just secant squared. So derivative of sine x is cosine of x. Derivative of cosine of x is negative sine of x. And as we just established here, the derivative of tan of x is secant squared of x. And there you have the 3 basic derivatives for the 3 basic trig functions. And now we can use those, obviously, with conjunction to what happens if we are dealing with the sine of a function. Not just sine of x, but the sine of a function. So if I had, for instance, the sine of 3x, and I wanted to find its derivative, or if I had the tangent of 5x plus 2, how would I find that derivative? Again, just like it has been with the exponential functions, with the log functions, it's just an application of the chain rule. So we're going to look at sine of f of x. We're going to say u equals f of x, and y equals the sine of u. So we're going to first find dy du, and then du dx. So basically, if I'm looking at the sine of f of x, I'm going to take the derivative of the sine of u. That becomes cosine of u. And then I'm going to multiply that by the derivative of what that f of x function is. And then I can just come back in and plug back in what u was. Right? And that's going to be true for sine of f of x. That's going to be true for the cosine of f of x and the tangent of f of x, as we see down here at the bottom. So if you start with the sine, you're going to have the cosine of f of x times the derivative of the inside. If you have the cosine of f of x, it's going to be negative sine of f of x times the derivative of what was inside. Same thing with tangent. You have tangent of f of x, you're going to have the secant squared of f of x times the derivative of f of x. Okay. So let's go ahead and get into some practice with these so that we can understand what's going on. Now, if we look at x times the sine of x, this one's not so bad. It's really, as you can look at it, you should be able to identify, this is really just the product rule, because we have x times the sine of x. So when we look at that, we want to say, okay, u is x, u prime is 1, v is the sine of x, v prime is going to be the cosine of x. So we can just plug in there, the product rule says u prime times v plus u times v prime. So I have 1 times sine of x plus x cosine x. Nothing more I can do to simplify that. Done. Over here we have 4 tan squared of 3x. All right. So here we see we have an f of x inside there. All right. So when we look at this guy here, the first thing we want to identify is we should rewrite 4 tan squared 3x with these square brackets. So that we understand it's really the tangent of 3x that's being squared. So now I look at it and I say I could rewrite this as 4u squared, where u equals the tangent of 3x. And we have a couple of things going on here, because not only do we have to do the chain rule, we also have to remember how to take the tangent of 3x as well. So we'll start with this whole dy du part. Now dy du, 4u squared, that derivative is just 8u. And we'll come back and plug in, as you see in the next step there, what u is. The next part we have to take du dx, and that's going to be taking the derivative of the tangent of 3x. Well, we know the derivative of tangent is secant squared, so I can go ahead and plug in cosine squared of 3x on the bottom, and this numerator part here, that's the derivative of the inside part. So that's the derivative of the 3x. Now, the reason that all this is helpful is because now I can put it all together, and I have 8 tangent of 3x times 3, so I have 24. And then on the bottom I have cosine squared of 3x. Now, because I look at it as tangent is sine over cosine, another way to think of this is I have 8 sine 3x over cosine of 3x. And that's going to be times 3. I'll just put this 3 out front here for now. Over cosine squared 3x. So because I have cosine of 3x, pick up the color here, right there, and I have cosine squared 3x right there, I can just move that down, and that's why I have my cosine cubed of 3x that we see there. Generally, we like to get things back in terms of sine and cosine if we can when we're simplifying with these trig functions. All right, a little bit more challenging in exercise B there, but not too bad if you take your time and kind of go through what's going on. Now, let's take a look at the cosecant of x, the secant of x, and the cotangent of x. If we look at the cosecant of x, remembering that cosecant of x is really just 1 over sine of x. Well, now we can just use the chain rule to find the derivative of the cosecant of x. Just refer to u as the sine of x. Now we really have y equals u to the negative first. Now what we know is that the du dx, the second part of that chain rule, the derivative of sine of x is just cosine of x. So when we go through and we plug in, we have the derivative of u to the negative first. That's negative 1 times u to the negative second. So that's where we have the negative 1 over sine x quantity squared, or sine squared x. Then we have to multiply it by du dx, and we know du dx is just cosine x. So now I have negative 1 times cosine of x over sine x sine x. And if I think about that, that is just one of our trig identities as well. And we can say that the derivative function is negative cosecant x, cotangent x. All right? Because I have negative 1 over sine x, that's negative cosecant x. And when I have cosine x over sine x, well, that's just cotangent x. And we could go through and do that same exploration for secant of x and cotangent of x. And what we would end up finding is that when we have the secant of x, its derivative is secant of x tan x. And for cotangent of x, we're going to have negative cosecant squared of x. Or in a nice neat table, as we see here. Again, just like sine, cosine, and tangent, the derivative functions for cosecant, secant, and cotangent are also available for you on or in your formula notebook. So don't feel that you have to memorize these, although after doing a few problems, you probably will memorize at least some of them. All right, let's do a couple of examples with these more advanced trig functions here. If I'm looking at the cosecant of 3x, I'm going to follow the same rule that we did previously. We're going to think of this as one function, and then we're going to take the derivative of the inside. In other words, we're going to apply the chain rule. So if I have the cosecant of 3x, first thing I'm going to do is I'm going to look at, okay, it's the cosecant of x. So the derivative of the cosecant of x is negative cosecant of x times the cotangent of x. So I have negative cosecant of 3x, that's my f of x, cotangent of 3x, and then I need to take the derivative of the 3x, which the derivative of the 3x is just 3. Now don't be confused by the negative. That negative is really just what came down from what we had previously. So that tells us that the derivative of cosecant of 3x is negative 3 cosecant of 3x, cotangent of 3x. When we look at example B here, all right, same idea, except we're also dealing with the fact that we really have the cotangent of x over 2 raised to the 1/2. So this is kind of like a chain rule within a chain rule. So we start by rewriting, making it raised to the 1/2. Now we look at it, we're going to apply the chain rule first. The chain rule tells us that I'm going to multiply by 1/2 into the front. Don't forget, you have to drop the exponent by 1. Then we're going to multiply by the derivative of what the inside was. Okay, so derivative is, we're looking for the derivative of the cotangent of x over 2. Well, we know the derivative of cotangent is negative cosecant squared. Put the f of x in, multiply by the derivative of the inside. So again, this is a chain problem within a chain problem, right? And then we just have some rewriting to do. For instance, when we look at this piece here is raised to the negative 1/2, that puts it in the square root in the denominator. This negative cosecant squared of x over 2, that's going to stay on the top. Then I have my 1/2 times my 1/2, which is 1/4, which is why we have that 4 in the denominator. All right, so we talked a lot about the trig functions today and their derivatives, and that's what we did. Our goal was to find the derivative of all 6 trig functions, and we did that, and we'll be practicing more with that in class.